And that brings us to our feature presentation with Jeremy Couturier. I don't know if I'm getting that right. Who is a French postdoc at the University of Rochester working on celestial mechanics, and his presentation, A Journey into Saturn's Rotation. Why is it so tilted? And I'm going to let him come up here and switch to his presentation, and we'll go from there.
So I have a French computer, and I forgot to bring the adapter to charge it, and I have 28% battery, so I will have to be pretty quick. Oh, it will just switch off.
Would it make any sense to? Do you have a copy of his slides? No. You want to put a copy of your slides on my?
Yeah, and if you
flash
can,
drive,
if you can
and then
set up, so if you
yeah,
we can switch directly.
Yes.
So just before, because I have 28%, there is no way.
Yeah.
And, it won't hold.
So to fill everyone at home, we have a laptop battery power issue, and we're taking some measures here to mitigate that problem.
So I will need that.
It's a good thing we're a technology club.
Okay. So here is the So I will start the presentation normally, and if we have battery issue, and we will have battery issue, then we will switch computer. So I'm going to talk to you about the planet Saturn, and in particular, we will be focused on the rotation of the planet Saturn. How is it rotating in space, and why is it rotating this way and not another way? And especially this presentation will be about the different steps that scientists have to take in order to understand some dynamical motion in the solar system. And as you can see, it's generally not very straightforward. So the first awareness of planet rotation, it basically happened basically at the time where we were able to see planets in another way than just a dot in the sky, because if you don't have an astronomical lens, all you see is a dot. So the dot might be rotating, but you can't see it. So the first to point something toward the planet was Galileo Galilei in the 17th century. And he was able to discover the Galilean moons. He was the first to see them. And his lens was of pretty bad quality, so he was not really able to see details on the surface of planets, so he was not able to interest himself to the rotation of planets. And then a few years later, when I say a few years later, it was actually 1 century later, but anyway, so Giovanni Cassini, with a lens of better quality than that of Galileo Galilei, he was able to see details on the surface of planets. So in particular, he observed Mars, Jupiter, and Venus. So obviously, he was not seeing pictures of this quality, because these pictures are from the spacecraft we sent in the solar system. So the picture of the planet he had was not of such quality. But the idea is that for Mars, there is basically no atmosphere on Mars. So even if you don't have such a good quality telescope, he was still able to see like some shade in the color, or some bridge on the planet of Mars. And furthermore, Mars is a planet that is orbiting the sun outside the Earth. So it's possible that Mars is visible all night long. So if you take your telescope out and you observe Mars all night long, and if your telescope has such a quality that you can observe bridge, then you might be able to see Mars rotating around itself. And that's what Cassini did. And he was able to determine that the rotation period of Mars is a little bit more of 1 day. It's 24 hours and 40 minutes. And the accepted value today is really close to that. For Jupiter, the same. You can see the red spot. So he was able to determine the rotation of Jupiter. And then there is Venus. You also observe Venus. Venus, it's harder because it's inward in the solar system with respect to us. And actually, Venus has a huge atmosphere. The atmosphere of Venus is 100 times thicker than the atmosphere on Earth. So from the surface of Venus, you can't see past the atmosphere, and so we can't actually see the surface of Venus. What we see is the cloud cover, and as you can see, like Venus is very one color. So with the pretty bad telescope he had, it was very difficult for him to see details on the surface of Venus. Here is a little drawing he made in 1677 about his observation of Mars, but basically, he had a really hard time determine the rotation of Venus. But still, he gave us a value of a little bit less than 24 hours at that time for Venus. And then there were further measurements for the rotation rate of Venus. So then there was Blanchini that said, no, it's not 24 hours, it's 24 days. Okay. And then the son of Cassini also take on the step of his father. He said, okay, it's 23 hours and 20 minutes. And then we had Schroeter the same year. No, I don't think it's the same year. I think I just forgot to change the year when I made the slide. So this year is probably wrong. But Schroeter was like, okay, no, it's 23 hours, 20 minutes and 19 seconds. And then 1 century later, we were like, the huge precision. So I have 20% remaining batteries. We will have to change computer at some point. And the Vico was like, okay, it gave us a value precise to 10 to the minus 4 seconds. So I have no idea how he managed to get such precision, given that we can't even see the surface of Venus. And then in 1980, Giovanni Schiaparelli, he said, no, it's none of that. The rotation period of Venus is 224.7 days. So we went from 23 hours to 224 days. And so how did he manage to get such a result, and why is it so different from from other people with us? So, well, a few years before, so George Darwin, he studied tidal forces, and he determined that the moon was synchronized with the Earth. So the rotation period of the moon is the same as its orbital period. It's because it is synchronized to Earth due to tidal forces. And at that time, we thought that Mercury was also synchronized with the sun. And so Schiaparelli said, I think that Venus is synchronized with the sun. And since the orbital period of Venus is 224 days, its rotation period should be that same value. So it gave us this value. And then we had to wait 1964, because at that time, the technology had progressed. We had radar, and with radar, we were actually able to see the surface of Venus. We sent some ray for which the atmosphere of Venus is transparent, so we can see the surface of Venus. And we were able to see that the rotation of Venus is 243 days. And actually, it's minus 243 days because, contrary to the other planets, Venus is not rotating like that. It's actually rotating like that in the other side of all the other planets, which is why we have this minus sign. So as you can see, the rotation period of Venus, we actually we took from 1667 to 1964 to get it right. And the other thing that you can notice is that observers and scientists, when they are trying to get results to understand how is science working, they have a preconceived idea. Like all these guys, Bianchini, Cassini, Schroeter, De Vico, they were persuaded that the rotation period of Venus, okay, it was like something a little bit less than 24 hours. And so somehow they managed to see details on the surface of Venus that did not exist to give such precise value about the rotation period of Venus, while they were completely wrong. Now, what about the top? Because, okay, planets are spinning, but tops are spinning too. And maybe there will some similarities between the top and the planet. So here you have the nice top in the Inception movie that maybe you saw. So what about the motion of a top? And now there is a nice little GIF that I'd like to show you. So now when you look at these two tops, so they are rotating around themselves and we can't really see this motion. It's going really fast. Like these two tops are probably performing 20 rotation per second. But as you can see, they are also precessing. There is a precession motion. If you look at the axis of rotation of the top, it's doing like that. And it's doing that much slower than the top is actually rotating around itself. So actually, it looks like we have two components in the motion of the top. There is the rotation of the top, but also the tilt of the top is rotating around the vertical at a frequency which looks much less than the actual frequency of rotation. So now let's look at this little schema here. So so you have the top, so it has some axis of rotation, and we'll just need three angles. This angle theta is just the angle of the top. So for example, on Saturn, this angle makes a complete rotation in 10 hours, a complete tour around Saturn in only 10 hours. And then there is some tilt, and maybe Saturn is tilted. And actually it is tilted, and we will see that it's not normal that it is, and we will understand why it is tilted. And there is a precession motion. This angle here, which is C, that you see here. So that's the angle that the top makes, that the axis of rotation of the top makes with respect to some reference here, and it's rotating around the vertical, much slower than the top is rotating around itself. Okay, so if the top is rotating like that, Saturn should also rotate like that. Like there is no reason that if tops do this, planets should do that too. So let's get back to. So for Saturn, so you have Saturn, and Saturn is also tilted. Like the vertical is defined with respect to the orbital plane of Saturn. So that's the orbital plane. That's the sun. And so that's the vertical. This little arrow is the vertical, and this arrow is the axis of rotation of Saturn. And so you have some angle, which we call the obliquity or the tilt. Generally, it is noted by this variable epsilon. And if the top is precessing, Saturn should be precessing too, and actually it is. Now let's have a look at the obliquities in the solar system, the tilts in the solar system. So Mercury is basically not tilted, it is vertical. Venus, it is 180 degrees because it has a retrograde motion, as we see. But basically that means that it's not tilted, it's just like upside down, but it's not tilted really. The Earth and Mars have pretty much the same obliquities, but these obliquities were chaotic in the past. It was proved by Jacques Lascar in 1993. So basically we could have pretty much any value, and it's not surprising that we have these random values. But what was shown by Lascar and Rochester in 1993 is that the obliquities for the giant planet, Jupiter, Saturn, Uranus, Neptune, they should be primordial. In other words, they shouldn't have changed since the formation of the gas giant. And we expect planets to form with near zero obliquity. We expect planets after their formation to be like vertical. And if you look at, so okay, Uranus and Saturn are also tilted, but we pretty much know why they are, and we are not interested in these two planets. We are interested in Saturn. Why is Saturn so tilted? Jupiter is not tilted, and it's in accordance to what we would expect from a giant planet, but Saturn is very tilted. It's actually more tilted than the Earth with an angle of almost 27 degrees. So why is it so tilted? So first, what do a top and Saturn have in common? So if you look at these two pictures, you have the top on the left, Saturn on the right. Can you find any similarities between the top and Saturn? I asked the audience looking at these two pictures. What do you say?
They have a ring.
Yeah, so actually Saturn has a ring, but like forget about the ring, forget about this dot which is the satellite, and forget about the ring. Just look at Saturn, like, and look at the top.
Most of the mass is the Saturn.
Yeah, like it has an equatorial bulge. It's flattened, and that's what they have in common. And that's actually why they have this precession motion while the axis of rotation is rotating like that. So they have an equatorial bulge. So Saturn is flattened because it's rotating quickly. 10 hours is really is a short rotation period for a planet. And the top, it has an equatorial bulge just because it was built like that. And now, in the case of the top, when you put it on the table and you make it spin, the Earth is pulling on the equatorial bulge. And in the case of Saturn, it is the sun which is pulling on the equatorial bulge. And if something is spinning and you try to pull on its bulge, it's just make it precess and then has its precession motion like that. So that's what happened for the planet Saturn and for the top. Actually, if we just have a look at the equation that determines how fast this precession motion is going. So here epsilon is just the tilt of it's the tilt, and theta is the angle of rotation. So dot theta is how fast the top is spinning. And as you can see, is that the fastest the top is spinning, and the slowest it is precessing. And if you look at the top, when you start just spinning it, at the beginning it has this precession motion, but it is slow. And when the tops get tired at the end, because it lost energy due to friction against the table, it's rotating not as quick at the end. So this denominator is decreasing. So the precession motion is accelerating, and that's what we see on the top. Like at the beginning, it's processing slowly, and then in the end, just before it falls on the table, it's processing much quicker. That's because here the spin rate, it's in the denominator of this equation. Now it depends on the mass of the top, acceleration due to gravity. This is the inertia of the top. And it also depends on the obliquity, and cosine of the obliquity decreases as the obliquity increases. So when the obliquity increases, when the tops gets more tilted, it also processes slower. And that's the same for Saturn, because for Saturn, you can still see that the precession frequency is proportional to the cosine of the tilt. And if for some reason the rotation rate of Saturn were to decrease, we would also see that the precession accelerates. So actually, we have a lot of similarities between the dynamics of the top and the dynamics of Saturn. So if you evaluate this quantity, you find that for Saturn, a complete rotation of the axis of rotation takes 7 million years. So while it rotates around itself in only 10 hours, it takes 7 full million years for the axis of rotation to complete a rotation. But this simple dynamical model, it doesn't explain why the tilt increases, because when you put a top on the table, the tilt doesn't increase. While it's processing, the tilt stays constant. Only at the very end, when the top lost a lot of energy due to friction against the table, okay, the top just completely falls on the table, which is an increase of the tilt. But we don't have such equivalence with Saturn, because Saturn is in space, it's not against the table, it's not losing any energy, so the tilt should not be increasing. So why did it increase? So actually, I said the period was several million years, but if you take into account the fact that Saturn has a moon, which is Titan, Titan is orbiting around Saturn, and as far as the sun is concerned, it's as if can we change computer before this one turns off? So I'm really sorry to the audience. We will need a few minutes just to change computer, because this one will just switch off. Okay, so we are basically here. Okay, so Saturn and the top both have an equatorial bulge. Saturn because it's rotating, and due to the pull of the sun on the equatorial bulge of Saturn, Saturn has this precession motion. That takes several million years to complete the full rotation if we neglect the presence of Titan. I changed that a bit, wouldn't change. Okay. It's not working.
Just trying to open some Adobe thing there at the bottom in orange. Right click the orange one and close
Yeah,
it.
the orange one.
No, that,
No,
that one.
Yes. Okay,
No.
Quit on that.
Close on that. Close now.
So it eventually opened in all.
You
this.
opened it all, yeah, just took a while.
I think it's open in 3 or 4 different.
Yeah, because we
Uh-huh.
opened it like that many
No, that
times.
was all, okay.
It just took like 10 full minutes to open.
Like I said, if they're buying a faster computer next time.
Okay, so now it looks like I can even
yeah,
change.
now that all that other
Yeah,
stuff.
all this other stuff is.
Okay, not too, but I can change slides. Okay, it was so slow because trying to open it like 5 times on Adobe. Okay, and so we actually passed this slide when we saw that the expression for the speed of the wobble motion of the top is pretty similar to that of the wobble motion of Saturn. In both cases, a faster spins means a slowest precession motion, and a larger tilt also means a slower precession motion. So if you take this expression, you find that Saturn takes 7 million years to complete a full, for the axis of rotation of Saturn to complete a full rotation around the vertical. And in the case of the top, due to the loss of energy of the top, the tilt also increases slowly as the precession happens, until at some point the top falls onto the table. But we don't have such analogous in the case of Saturn, which is not losing energy a priori. The spin of Saturn is not decreasing. There is no loss of energy. So how can we explain the tilt of Saturn that increased from near zero at the formation of Saturn to today's value? So the 7 million years are actually only 1.8 million years if you consider the largest satellite of Saturn, which is Titan. And why is that? The reason is that if you look at this expression, here G2 is just a parameter that tells how flattened is Saturn. And in fact, when you have Titan rotating, it's as if Saturn was flatter, because I mean, it contributes to something that the sun can pull on. And the same for the G, it's the moment of inertia. If you have a satellite and Titan is locked into the equatorial plane of Saturn, so the sun can pull on the equatorial plane of Saturn. It can also pull directly on Titan, which in turn pulls on Saturn. So basically, you change these 2 parameters, which means that when you consider the presence of Titan, the largest moon of Saturn, this precession happens on in 1.8 million years and not 7. So now we will get to the explanation as to how the tilt increases. So it's a bit more complicated, and it's a question of resonance. So what is a resonance? So a resonance is when 2 phenomena happens at similar frequencies. Like if you imagine a child balancing in the park, and if somehow the child kicks himself on the while it's balancing at the same frequency it is balancing, then you will have the motion, the amplitude of the motion, which will be increasing. And there are a lot of cases where we have that in real life. If you imagine you have a spring, like a large spring, and if you're exciting the spring at the right frequency, you can see the spring having large amplitude motion, even though you're just giving small excitation to the spring. But if you excite the spring with the same frequency as the springs tend to move when it's left alone, then you have resonance. And so, okay, for example, imagine the top of the the top on the table. So if we look at the GIF that I can't show you because I won't even try to open them, but you saw the GIF a few minutes earlier. And okay, while the top is rotating very fast, this position happens slower. Let's say it was making a full rotation in 1 second. Now imagine you take the table and with the same frequency as the top is precessing, you give some motion to the table. You will be able to control the top. And now imagine, we go back to this equation, and imagine that, okay, you find the right frequency, you're able to take control of the top. And now we see that if the tilt increases, that means that this motion happens slower. So now imagine you capture the top into the resonance, and then ever so slightly you decrease the speed with which you will make the table move. Then you will force the top to tilt, because since the top is captured into the resonance, the top will want its precision to match the speed with which you're moving the table. And if you're moving the table slower, then you need to decrease the cosine of the tilt. So you need to increase the tilt in order for the cosine of the tilt to decrease. So you can capture the top into resonance if you're doing at the right speed when you move the table. And then ever so slightly, you don't want to be too fast, because if you go too fast, then the top will just exit the resonance and you won't be controlling the top anymore. But if you do this like ever so slightly, you will be able to tilt the top and make it fall. So for Saturn, maybe some guys was able to capture Saturn in resonance and make it tilt. And so who is some guys? Well, as we will see, some guys has a name called Neptune. So, okay. Saturn takes 1.8 million years to make this position motion. So if for some reason we're able to move the table with a period of 1.8 million years, so if there are in the solar system some excitation frequencies that happens on the period of 1.8 million years, then we might have an explanation for why Saturn is tilted. First, we need to have this frequency. And then for some reason, this excitation frequency, which we still don't know, but I will come to it, it needs to have decreased. So it forced the tilt of Saturn to increase. So now let's look at the frequencies in the solar system. So here S, imagine a planet, so Neptune, it is orbiting the sun on some plane. And due to the interaction with the other planet, the plane of Neptune is also having this position motion. So while the equator of Saturn is making this position motion, the full orbit of all the planets is also having the same motion. So the plane of Neptune is precessing in the same ways as all the orbital plane of all planets do. But when you look at Neptune, the frequency of this motion pretty much matches the frequency of the wobble of Saturn. So Saturn's, the axis of rotation of Saturn is wobbling at the same frequency, or if you'd rather prefer at the same period, than the orbital plane of Neptune is doing this precession motion too. So actually here, the guy with the table is just Neptune. Neptune is exciting Saturn. So earlier in the history of the solar system, Saturn got trapped into the resonance with Neptune. Then, for some reason, the frequency of the wobbling of Neptune it decreased, and so that forced Saturn to tilt in order to match the frequency, because we want to decrease the cosine of the frequency if this frequency decreases, which means we need to increase the tilt. So Saturn got tilted from near zero to its current value of 26 degrees. Okay, so there was a capture in resonance, but if you only capture the top and then you just stay at the same frequency, you won't tilt the top. If you want to tilt the top, you need to decrease the frequency. And so how does that happen? Why would the frequency of the precession of the orbit of Neptune would decrease? Well, it is due to the migration of the planets. So as you maybe know, planets were formed where some. So the sun was formed when some gigantic cloud of gas collapsed gravitationally, and then there was stuff orbiting the sun, and this stuff accreted, and that formed the planet. And then you have the planet, and there is this grand tack hypothesis that was elaborated during several years by these people, where you have planetesimals here. So that's the very early stage of the solar system. Here you have Jupiter, Saturn, Uranus, and Neptune. So Neptune is here. And here at the very, very beginning of the solar system, it was only 8 astronomical units away from the solar system. Today, it is 30 astronomical units away from the solar system. And then these planetesimals, they fall toward the inner solar system, and they got like in front of the gas giant. And because of the conservation of the angular momentum, every time a small planetesimal gets into the inner solar system, there is some recoil motion from the gas giant because you want to conserve the total angular momentum. And so the gas giant, at the very beginning, they got closer, and then they got farther away from the sun. And Neptune, from an initial distance of only 8 astronomical units, it reached the current value of 30 astronomical units. So today, Neptune is much farther away from the sun than it was in the past. And actually, this motion of Neptune, it depends on how close it is to the sun, because if it's closer to the sun, it's also closer to the other planets. And the interaction between Neptune and the other planets is why Neptune is doing this motion. But if Neptune got farther away, this motion decreased. So Neptune captured at some point, it was getting farther away until the frequency matched the wobble motion of Saturn. So there was capture and resonance. But then as Neptune was migrating slowly enough, it was the same analogous as us on the table, ever so slightly diminishing, decreasing the frequency with which we move the table. And so that forced the tilt of Saturn to decrease. And so in the first paradigm that was developed by Hamilton and Ward in 2004, the explanation is that Neptune migrates, it captures Saturn into resonance, it keeps migrating, so it's doing the orbital plane of Neptune is doing this motion slower, with a slower frequency, and Saturn wants to match the frequency, so it increases its tilt, so that in the expression that we saw about the frequency of the precession, the cosine decreases. So we keep the match. And then, so I will go quickly over these figures, but basically they are extracted from the paper from 2004 of Hamilton and Ward, where here you see the obliquity. So this is the right scenario. So in this scenario, what you see is that, okay, that's the formation of the solar system. Then 100 million years after that, Neptune captures Saturn into the resonance. And then Neptune keeps migrating until it reaches its current and definitive value of 30 astronomical units. When it reaches the 30 astronomical units, Neptune starts migrating. There are no more planetesimal to give some recoil motion to Neptune. So the wobble motion of Neptune doesn't change anymore. So Saturn has no more reason to tilt. So Saturn reaches its current value of 26 degrees, and it just stays that way up until today. So in this scenario of Hamilton and Ward, the tilt of Saturn occurred like pretty much soon after the formation of the planets, only 100 million years after. It lasted for a few 100 million years, and then no more evolution. So if you can resume, like you have the formation of the solar system. The grand tack hypothesis with Neptune that migrates. So Saturn tilts between the capture and resonance, which happened between 10 and 200 million years. And then at 200 million years, Neptune stopped migrating. So Saturn stops tilting even further. And from 2 million years after the formation of today up to today, you have no more evolution. The tilt of Saturn stays constant. But it's not what happened. And it was understood much later, I mean, 17 years later, only 2 years ago, by a team of French scientists. It didn't happen like that. The idea is like, if you remember Titan, so Titan is changing the frequency with which Saturn is doing this motion. And actually, the contribution of Titan, it depends on how far away Titan is from Saturn. So Titan contributes to increasing the wobbling motion of Saturn. But what if for some reason, in the same way that Neptune migrated away from the sun, maybe that Titan also migrated away from Saturn? And actually it did, and a lot. And so the idea is that in the early solar system, 2 million years after the formation of the solar system, the tilt of Saturn, it did not take 1.8 million years. It was much, much longer than that, because Titan was much closer. And if it's closer, it does not bulge outward as much. So the sun has less to pull on. So Saturn is doing this motion, but slower. And so there is no capture in resonance, because in the early solar system, Saturn was doing this much slower than the orbital plane of Neptune was doing this. So no capture in resonance. Actually, the table was just moving too fast, so nothing happens. If you move the table very fast when the top is spinning, all the top sees is some averaging motion, and that's it.
He's gonna lie on his favorite pillow, period.
Who is speaking?
I thought I heard Jackie.
Jackie, use your microphone.
But why would Titan get farther away from Saturn? So in the case of Neptune that gets farther away from the sun, it's the planetesimal that falls in the inward system, and so that gives some recoil motion to Neptune. But for Titan, it's just tidal effects. So Titan is rotating on Saturn. So here you have Saturn, and here you have Titan. And Saturn, it only takes 10 hours to make a full rotation around itself. But Titan, it's taking longer to turn around Saturn. It takes, I don't remember, I don't want to give you wrong values, but it's taking much longer than 10 hours, probably 1 day or 2 days or something like that. Which means like, okay, Titan is here. It pulls on the material of Saturn. So it raises a little bulge here on Saturn. This is a little bulge. But then after it raises the bulge, okay, it keeps rotating, but less than Saturn rotates. So the bulge, it ends up being a little bit in front of Titan, because Saturn is rotating faster than Titan is orbiting around Saturn. So what Titan sees is the bulge that it raised, but not below it, a little bit in front. Then by gravitational interaction, Titan here is pulling on this little bulge. And so if you imagine here Titan pulling on this bulge, then you decrease the rotation period of Saturn. So the rotation period of Saturn decreased. And if you remember the formula, it's already an explanation as to why the tilt would change. But actually, Saturn is so much more massive than Titan that the rate by which Titan is changing the rotation speed of Saturn is completely negligible. But you need to conserve the angular momentum. I mean, Saturn, when it's rotating, it has some angular momentum. If Titan is decreasing the rotation rate of Saturn by pulling on the bulge, then where goes the angular momentum? Well, it goes in the orbit of Titan. And an orbit has more angular momentum if it's farther. So when it pulls on the bulge, Titan decreases the rotation rate of Saturn, but it also gets farther away from Saturn. And the same is happening with the moon. The moon is doing the same on Saturn. And you might not know it, but each year the moon is 2 centimeters away, farther away from the Earth that it was the year before that. And in 1.5 billion years, we will lose the moon because it will just escape the sphere of influence of the Earth, and it will just get captured by the Earth. It will just become not another planet, but like a big asteroid. And so it's the same is happening with Titan. As Titan is not getting farther away from Saturn at 2 centimeters per year, it actually happens at 13 centimeters per year. Okay, it's not much in 1 year, but since the early solar systems, that actually means that here you have the distance from Titan to Saturn. Today is 21 Saturn radii. but in the early solar system, 4.5 billion years ago, Titan was only 6 Saturn radii away from Saturn. Which means that the bulge of Saturn was less. The sun has less to pull on Saturn. And this motion of Saturn was slower, pretty much slower than here. So here, that's basically, that is what is in front of the cosine of the obliquity in the formula that I showed earlier. And so the frequency of this wobbling motion is just this constant alpha times the cosine of the obliquity. And in the past, this precession constant, it was much smaller because Titan was much closer from Saturn. And this frequency, it was not like 0.8 arc second per year as it is today, it was only 0.3, which means that these, for the axis of rotation to complete a full rotation, did not take 1.8 million years, it was rather 5 million years. But here you have Neptune that basically did not migrate because Neptune stopped migrating after 200 million years. So here, S8 here is the frequency of this motion from Neptune. So as you can see, in the early solar system, this motion of Neptune, it was just too fast. You could not have capture into resonance. If Saturn is the top and Neptune is the table that's moving up and down, in that case, in the early solar system, the table was moving up and down too fast. But then Titan migrates away, and so Saturn starts doing it much and much faster until 1 billion years ago or 1.5 billion years ago, we reached the match between this motion of Neptune and this motion from Saturn. And then there is capture into resonance. And after there is the capture into resonance, okay, Neptune does not change this motion, but Titan keeps migrating away, which means that if Titan keeps migrating away, Saturn wants to do this faster, but it can't because it is trapped in the resonance. So if Titan is getting farther away, it means that you are increasing this constant. And the precession motion of Saturn, it is this constant times the cosine of the obliquity. So how do you keep match of Neptune's motion and Saturn's motion? Well, then you have to decrease the cosine of the obliquity, which means that you have to increase the obliquity. So because Titan is getting farther away, is this constant here? Maybe you don't remember the formula. Let's have a look. Let's have a quick look at the formula. So the speed at which Saturn is doing this motion is some constant alpha times the cosine of the obliquity. And in alpha, you have here G2, which is the size of the bulge, and C, which is the moment of inertia. And these quantities, they change as Titan migrates away, which means that alpha is increasing. And if you increase alpha, you would increase the wobbling motion of Saturn. It would go faster. But since Saturn got trapped in the resonance with Neptune, it can't get any faster. Now it's locked. And if you want to keep this quantity constant, and this quantity here is increasing due to the migration of Titan, then you need to decrease this quantity. And if you want to decrease the cosine of the tilt, you need to increase the tilt. And so that's why Saturn is tilting. And if you remember on the first slide, it was not alpha that was changing. Alpha was constant in the first paradigm of Ward and Milton, but it was Neptune that was going slower and slower. So we needed to diminish this quantity. And since alpha was constant, it was the cosine of the obliquity that was diminishing. And so the tilt that was increasing. But that stopped after some point when Neptune stopped migrating. But Titan does not stop migrating. It's still getting farther away from Saturn at a rate of 13 centimeters per year. So not only that explains the tilt of Saturn, which tilted from 0 to 26 degrees when it got captured into the resonance, but since Titan is still getting farther away, Saturn is still tilting. Actually, it's what it's what these guys, this team of French scientists, thinks. So to resume, So this is the capture in resonance. So here you are 4 billion years ago. So nothing happens because 4 billion years ago, the precession motion of Saturn was too slow. But then some 1 billion years ago, Titan migrated enough for us to get capture into the resonance. And so here, due to the capture and resonance, you see the tilt of Saturn that is increasing. And it is still increasing as of today. Like today we are here, but in the past we will be here. And you see the tilt that increased. So according to this little diagram, in 1 billion years, we should expect the obliquity of Saturn to be 40 degrees instead of the current 26 degrees. Because we are trapped in the resonance. And since Neptune does not want to go any faster, and since Titan is migrating, Saturn has to tilt in order to keep the match between the motion of the wobble of Saturn and the orbital precession of Neptune. So that's basically the same figure. And here, it's all a green range. It's not a single curve because we have actually a large uncertainty here in this formula. We have a large uncertainty on what is the moment of inertia of Saturn. Actually, we had a large uncertainty up until 1 year ago. We knew this value by 10%. So we knew the precession frequency of Saturn by only 10%, which is why here we have a large uncertainty. So we can't actually be sure that Saturn is in the resonance, because if you want to be sure that Saturn is in the resonance, we need to be able to compute the precession frequency of the wobble of Saturn precisely. But since we only have 10% precision on the moment of inertia of Saturn, we can't. But we just assume that it was captured in the resonance because it was the best explanation as to why Saturn was so tilted. And so it was the paradigm of this team of French scientists. So to conclude, we have the ground tag, Neptune migration, but at that point, nothing happens for the tilt of Saturn because Saturn is not yet trapped into the resonance. Then you have no more evolution from 2 million years after the formation of the solar system up to 3 billion years, nothing happens. But at like 1 billion years ago or 1.5 billion years ago, which means 3 billion years ago after the formation of the solar system, then we get captured into the resonance, and then Saturn's obliquity starts to increase in order to match the migration of Titan. Okay, but there is still a problem. It's actually still not exactly like that it happened. So the first paradigm about the migration of Neptune was wrong because they forgot to take into account the fact that Titan migrates. And this second paradigm of the team of French scientists, there is still a problem because they think that Saturn is still trapped into the resonance. But then came wisdom with a paper in 2022 that actually showed that Neptune is not trapped in the resonance. Saturn is not trapped in the resonance with Neptune. So there is still a problem. So if you remember, we had a large uncertainty on the moment of inertia of Saturn, which meant that we could not compute with absolute certainty the speed of this wobble motion for Saturn. We only had it by more or less 10%, and it matched pretty much. And since the dynamical model suggested the capture resonance, we just assumed that, okay, it was in resonance. But then Wisdom et al., they made a paper in which they elaborated a model which allowed them to compute this moment of inertia really precisely, which allowed them to compute this motion from Saturn very precisely. And they were able to show that the system, even though it is close to the resonance, it is not in the resonance. So there is not this trapping. So what's wrong with the first model? Okay, so up until last year, we had a large uncertainty on the moment of inertia of Saturn. But there was something about Saturn that we knew very, very well, and it was the gravitational field around Saturn, because I think the Cassini spacecraft arrived at Saturn in 2005, and it stayed there until 2017. So from 2005 to 2017, the Cassini spacecraft, which has the same name as this guy we talked about earlier. This spacecraft, so it orbited Saturn, and by fitting the motion of this spacecraft, we are able to constrain very finely the gravitational field of Saturn. And actually, it is possible to relate the gravitational field to the moment of inertia. And this work was done by WISDOM. So WISDOM just assumes that Saturn is just a superposition of shells, and he chooses the densities and the radii of the shells so that his model of Saturn has a gravitational field that matches the real gravitational field of Saturn. So he's able to build a nice model of Saturn like that. And once Saturn is built in this model, well, he can easily compute the moment of inertia. And by doing so, he was able to give a value of the moment of inertia that's not precise by minus or plus 10%. He actually got like less than 0.1%. He was able to give a very precise determination of this moment of inertia, which in turn allowed him to say that no, we are out of the resonance, we are close to the resonance, but we are not trapped in the resonance, which means that currently the table is not going at the right speed. The table, which is Neptune. So that's just, so these are coefficients that are related to the gravitational field, and here we see the feat of WISDOM. So here's just the figures that shows how WISDOM and his team of scientists were able to fit the gravitational field of Saturn. And here, that's what he finds for this C value, for this angular momentum. Before, this angular momentum was very uncertain, but here his best fit is the red curve. And here the critical value, here the little black range, is the value that the moment of inertia of Saturn should have for Saturn to be trapped in the resonance. And as you can see, we are here. So we are close to the resonance, but we are outside. So somehow, the table captured the top, and it made the top, so the table kept getting at the same speed, but for some reason, the moment of inertia of the top, it changes, but that's because Titan migrated away, so that tilted the top. And then Saturn escaped the resonance, and it shouldn't have. So how did Saturn escape the table? How did the top escape the control from the table? So there's just another figures that shows that, okay, we are outside of the resonance. Well, the idea is that actually it's the idea of WISDOM et al. Before that, Saturn has had another satellite that doesn't exist anymore, and they call it Chrysalis. So around Saturn, you have Titan, and you also have some other satellites. And in the past, you also had a satellite whose name was Chrysalis. And so actually, when the top was captured into the resonance, when Saturn was captured into the resonance, Chrysalis was there. And in the same way as Titan does, Chrysalis also contributes to the bulge of Saturn, which the sun can pull on in order to precess Saturn. But if for some reason this satellite disappears, instantaneously, this precession motion of Saturn changes. And as I told you, if the table changes its frequency too fast, you lose the resonance. In the same way, if for some reason the tops start precessing much slower or much faster instantaneously, it will get out of the resonance. So it's what happened. And the idea is that there were some gravitational interaction between Titan and Chrysalis. This gravitational interaction, it destabilized the orbit of Chrysalis until Chrysalis got very close from Saturn. And when the satellite is orbiting very close from its planet, the tidal forces on the satellite are so strong, then they just break the satellite apart. So the idea is that Chrysalis was on some circular orbit around Saturn. it got destabilized from its orbit due to some interaction with Titan. It passed too close from Saturn. It was broke apart. And the remnant of Chrysalis are the current rings of Saturn, actually in the model of Wisdom Metal. And when Chrysalis broke up, well, basically it was not here anymore. So suddenly, the bulge that the sun used to see on Saturn, it changed, it decreased. And so the wobble motion of Saturn, it suddenly decreased. And this allowed Saturn to get out of the resonance. So that's some simulation. So here, that's the early solar system in the bottom. Here we get captured in the resonance. So here, that's still the same paradigm of the team of French scientists. We are captured in the resonance because Titan is migrating. And so the precession motion of the top of Saturn is changing. And Neptune captures the top. Then as Titan migrates away, the obliquity increases up to some value, which was probably, given their simulation, 36 degrees. But then Chrysalis breaks up. So suddenly, the precession motion of Saturn changes and Saturn escapes the resonance. And so we go from here to here. Where here, that's the precession constant. So we go left because Saturn, after the loss of Chrysalis, it started precessing like that, but slower. And so we escaped the resonance. And then the obliquity decreased a little bit, but now it's stabilized at 26 degrees and it's not increasing anymore. And so that's why we're so close to the resonance, because this breakup of Chrysalis, it happened only 100 million years ago, which also coincides with the current estimation we have about the age of the rings. So in this model, the rings come from this ancient satellite of Saturn that just broke up due to a close encounter with Saturn. Okay, so to summarize this last paradigm, so it's in the beginning it's similar to the second one, so Grand Tag, Neptune migration, but nothing happens because Titan is still too close from Saturn for the system to get captured into the resonance. And then 1 billion years ago, maybe 1.5 billion years ago, the system is captured into the resonance and Saturn's obliquity keeps increasing, and it would still be increasing today if Saturn had not lost a satellite. But 160 million years ago, that's their best fit, Chrysalis breaks up. This allows Saturn to escape the resonance of Neptune. So the top escapes the motion of the table, basically. So it stops tilting, and now Saturn tilted due to this past resonance, but now it's not tilting anymore. And it's stabilized with a tilt of around 26.7 degrees. So if you remember the beginning of the presentation, it was the long journey to just get the rotation rate of Venus. And there was a lot of trial and errors from the scientists. And we might think, okay, but it was like the past, now we are good at that and we don't make error anymore. But in fact, just understanding also why is Saturn tilted, it took us quite some time too. We had the first paradigm of Ward-Hamilton that was wrong. Then another paradigm of Science-Fest, Bouet, and this team of French scientists that was also wrong, or at least imprecise, because they thought Saturn was still trapped by Neptune, but it was not. And then this last work from last year of Wisdom and his team, that's for now the best explanation we have for the current state of the rotation of Saturn, but who knows, maybe it's still not the right explanation to why is Saturn tilted, and maybe we will have some change in the future. So I hope you like the presentation. It's now over. And I'm so sorry about me just forgetting about what I need to charge my computer.
Don't worry about it.
That's why we got backups.
And so sorry for using your computer.
Question.
Yeah.
Are there any thoughts or prediction on how we might verify the existence of chrysalis? Like whether we could take samples from Saturn's rings or?
Okay, so for now, the best we have is the presence of rings, because also in the past we did not really understand the tilt of Saturn, but we did not understand either why there are rings on Saturn, and in particular they are young. They are only 100 or so million years old, while Saturn is more than 4 billion years old. But now, in order to verify that the rings actually come from chrysalis, as you say, we will need to analyze more finely the rings. And there is still a problem because Saturn has a particularity. It is the least dense of planets in the solar systems. Its mean density is less than that of water. So basically Saturn weighs less than water, which is the only planet to verify that. And when a planet breaks a satellite up due to tidal forces, it's actually only able to break some things whose mean density is not much larger than itself. And since Saturn has a low mean density, it's only able to break the outer part of a satellite, which are less. And the inner part of the satellite are more dense because due to pressure, the center of celestial bodies are always much more compact and more dense than the outward parts. Like the outward part of the Earth has a mean density of 200 kilograms per cubic meter. But if you go to the center of the Earth, you already have 11,000 kilograms per cubic meter. And it was the same for chrysalis. And this model, even though it's, I mean, we like it, it looks nice, but if that's really what happened, then okay, we should have the ring, but we should also have the core of chrysalis. And we do not observe the core of chrysalis in the rings. So what happened? Maybe it just fell onto Saturn and was lost, or what happened? We don't know. So, I mean, it's a nice explanation. It might not be the or maybe two satellites collided and then we lost both of them. That's also a possibility. It's not the possibilities that preferred by the team of wisdom, because actually it's much more likely that satellites might get destabilized from its orbit and then it's passing too close from Saturn than two satellites actually colliding. Even when you simulate the motion of the solar system, planets getting ejected or falling on the sun happens much more often than planets actually colliding. So it's less likely. That's probably why they preferred this hypothesis, which is in itself more likely than the hypothesis that two satellites might have collided and broken up.
What about the mass? It's the mass of the ring, well, except for the core, you might be able to. Does the mass of the ring fit the resonance you needed to have chrysalis with Titan and all that mass?
Yeah.
It was the mass.
So according to the paper of wisdom, the mass of chrysalis should have been pretty close to the mass of Iapetus, which is the current satellite of Saturn. And the current mass of the ring is less than the mass of Iapetus. So it fits because obviously the mass can be more massive than the satellite itself. And as we say, since Saturn is unable to disrupt the core of chrysalis, if this is really what happened, then the mass of the rings should be pretty much smaller than the mass of chrysalis itself. And currently, the mass of the ring are pretty much smaller than the mass of Iapetus, which would have been the mass of chrysalis in the past. So if you only look at the mass, it coincides. But we will need to look at the composition, like do the composition of the ring really match the composition of other satellites of Saturn? Because all the satellites of Saturn, they come from the same rings of fragment and gas that collapse. So we don't know the current composition of the rings because we were not able to take samples. If we discover in the future that the composition of the rings does not match the composition of the other satellites of Saturn, then that will mean that this model of wisdom is probably not complete, or there is still something that we did not understand.
If you have an eccentric satellite, though, why would it make concentric rings? You know, the satellite, if something broke up and it was in an eccentric orbit, why does it make concentric rings?
So you mean circular?
Circular rings.
So, well, it's the same reason why all the satellites are circular, because So before it gets destabilized, the orbit of Chrysalis was circular, and then it became eccentric because it was destabilized. Which means that when it broke up, the rings were eccentric. But actually, the satellites, like in very early solar system, they were also eccentric. And why they got circular is due to this tidal effect that I was talking about. If you look at this tidal effect here, so one tendency of them is that the satellite gets farther away. It can actually also get closer if for some reason the satellite is orbiting the planet quicker than the planet is rotating around itself. Then in that case, the bulge will be behind. And so the satellites, by pulling on the bulge, it will increase the rotation rate of the planet. And by conservation of the total angular momentum, the satellites will get closer.
Isn't that happening with Phobos now?
Yeah, it's happening to basically all the satellites. And
Phobos
so-
is going down.
And so Phobos is going inward because Phobos has a very low orbit, and Phobos is orbiting around Mars in only 7 hours. But Mars takes 24 hours to complete a full rotation. So in the case of Phobos, if that's Phobos, then the bulge is behind. So Phobos is accelerating the rotation rate of Mars. So it's giving a little bit of its angular momentum to Mars. So it has to lose a small angular momentum by itself, which is why it gets closer. And we expect that in 100 or so million years, Phobos will get shattered by the tides of Mars, and Mars should get wings. And so this tidal effect, they also tend to circularize the orbits. So even if the rings were formed in the eccentric orbit, and they were probably, it's normal that they are circular today.
What about the age? You said the age of the rings. How do you guesstimate the age of the rings? The same orbital mechanics?
I have no idea. I know that the scientific community thinks that the rings are 100 million years old. I don't know how they know that.
Plus, if you think about it, anything that gets broken up is already close to the planet where it's going orbiting very fast anyway. So.
It looks like we have a question in the chat.
Yes.
Let's click on the chat.
Oh yeah. So the chat is here. So I clicked, but
You have to open up on the bottom. Where it says David.
I don't know why is this.
No.
That's funky.
Okay. Yeah, don't follow. I don't know what to do.
If you scroll to the top of the screen, you'll see the bar drop down. You can click on the chat.
Got it.
Well, so the question is how much of the mass of Chrysalis is left in the rings of Saturn? I honestly don't know. I know that it's less than the mass of Chrysalis because I know that Saturn can't disrupt the whole Chrysalis, but it depends on how much the center of Chrysalis was denser than the outward part of Chrysalis. So that depends on the equation of state of Chrysalis. And honestly, I don't know, but it is less, probably maybe half or less than half, I don't know. Yes.
Do we know the obliquity of any exoplanets at this point?
No. No, the reason is simple is that we don't actually see the exoplanets. We see signatures that left in the skies, which barely allow us to know that they exist. So we have no idea about their obliquities. We know, however, the obliquity of the stars because the star is bright. I mean, we don't know the obliquity, but we know the tilt between the axis of rotation and our line of sight. Like if you define the vertical as being perpendicular to our line of sight, then we know the obliquity of the star. And the reason is simple because the star is rotating, so it has some obliquity. And when we make Doppler measurement on the star, so first we see that the star is rotating because if it's rotating like that and we look at the left of the star, it's getting closer to us with respect to the right of the star due to the rotating motion. And if the planet is tilting, then you can also see the tilt by the Doppler measurement. So for stars, we know we have We know where there are axis of rotation points, not for planets.
Uranus is something like 80, 90, and it's really.
Yeah.
Does any of this apply to that?
So in the case of Uranus, actually, it was also resonance. So if you look at it was here. Yeah, so Uranus is a little bit more than 90 degrees, which means that in the case of Uranus, Uranus is lying down on its orbit. So it's orbiting the sun, it's basically rotating in like that. So there are models of resonance. So the specialist about the tilt of Uranus is Gwenal Boué. He's also part of the team of scientists that that elaborate the second paradigm, the one that thought that Saturn was still trapped in the resonance. And you can also explain the tilt of Uranus due to a resonance between a satellite of Saturn and some other frequencies in the solar system. So in that case, it would not be the wobble motion of Uranus that is trapped, but some orbital motion of the satellite. I'm not completely sure. It might be a resonance between how the orbit of the satellite is processing with some other orbit in the solar system. So you can tilt Uranus in this way, but it's actually unlikely. So it is thought for Uranus that maybe a large satellite was trapped by Uranus and maybe that tilted it. So
it's a collision.
So it might be a collision or just satellites that get trapped by Uranus because it's passing too close to Uranus.
Well, yes, low speed collision. Merger.
Not necessarily a merger. I mean, you don't have to have contact between a satellite and Uranus to tilt Uranus. But it's also a possibility. Because the idea is that Uranus is much less massive than Saturn. So you can actually, it's also rotating slower. So you can imagine that the giant impact might tilt Uranus. But this does not apply to Saturn because, okay, we have this nice model for Saturn, but the most obvious reason to why Saturn would be tilted is maybe just something hit Saturn. If you hit the top, you will also hit the top. You don't have to go to the table. So obviously they thought about that, but for Saturn, it's rotating really fast. Like imagine the top, if it's rotating really fast, then you just pinch it. You will affect it less if it's rotating fast. And it's also very massive. Imagine just a huge top, you will have to really push it to tilt it. And Saturn, due to it being very massive and spinning so fast, a giant impact seems very unlikely to tilt it that way, which is why we look at some other explanation. And in the case of Uranus, we can also explain the tilt by some trapping in resonance. But in the case of Uranus, an impact seems more likely than some resonance mechanism. It's actually what I think. Let's need to be verified. I'm not a specialist, but it is not Uranus. And for Neptune, the same. Neptune is not much more massive than Uranus, and it's not much tilted.
I just received a text that it's really getting nasty outside.
Ah.
Oh, good.
We will get buried in snow.
You might want to call it a meeting.
Yeah, if there's no questions, thank you very much.
So thank you everyone for attending. So I hope you liked it, even though it was a bit disruptive.
Thank you all for being here in this wonderful Rochester winter night.
Did anybody want to do chicken wings?
Not tonight.
I would love to.
Tonight.
You should-
Everybody drive safe.
Have a good night.
Good night.
Yeah, there was a question.
Thanks, everybody.
Okay.
So is Carol still here?
Yes, I'm here.
So to answer your question, so I think you're talking about so where's the slide? No, it's here.
Yeah, it showed the migration of the planets and some of the moons. I think you just passed it.
Yeah, so it's derived from both mathematical models and observation of Titan. I mean, if you just take into account the mathematical model, that's here the dashed curve. And it's only predicts that in the past Titan was a little bit closer from Saturn, but not by much. So you can derive more precise mathematical model that might explain a quicker migration. But now we have been observing Titan for several decades, and we're able to say that Titan is migrating very fast. So we fitted our model so that it matches the current migration rate of Titan. And I think that's it for the question.
It's clear.
I think Carol was talking about the 2 slides before that.
It's about to stop.
Oh,
the
two
Solar
slides.
system migration.
Yeah, for a while, there's a gap that.
But it's not.
Maybe a couple, maybe
Yeah, so
It's been off by about 2 hours.
that
That
one.
one, right there, right there.
Yeah, so this is the NIS model actually. So
No, I mean.
no, we don't have much observation for this because it happened several million years
How
ago.
long ago? Yeah.
In other words,
But it was derived like first in the early 80s, and now it's called the NIS model because it was derived in Nice by a team of scientists.
Okay, so it's got to be pretty well accepted.
I can't hear you.
Okay, thank you.
Okay, you're welcome.
The weather app is on.
Okay. So bye everyone.
Bye-bye, thank you.
You're welcome.
Good night, everyone.
Good night.
My son just texted me, thunder